We are now going to get into a discussion that will leverage at least the differentiation part of calculus for our business applications. And this particular set of methods is what is often referred to as unconstrained single variable optimization. Here's the idea. First, suppose we have a function, an objective function, where the x-axis represents one of the decisions we need to make, and the y-axis represents the score of how good or bad that decision is, where in this instance, the higher the value, the better. That is, good is interpreted as a higher value. I want to know what's my best decision to make. What is that value? As it turns out, if you notice, the slope of the curve at that point is equal to 0. Furthermore, you'll notice that, at least in the case of a maximum, that we notice that the change in the slope is moving from positive to negative. And the only way that that can happen is if the rate of change of the derivative, that is the slope, how the slope changes from left to right, is negative, because it needs to be negative in order to convert the slope from positive to negative, right? So a second thing that needs to hold true at this point is that the second derivative needs to be negative. In that case, then we say that x is a maximum. On the other hand, suppose that we say that we want to find the lowest possible value, in which case we're seeing the slopes change from negative to positive. And the only way that slopes can change from negative to positive is if the slope of the slopes at the x star is positive. And so in that case, if the derivative at that point is 0, which we see it is, and how fast those slopes are changing at that point is bigger than 0, we say x star is a minimum. This is what we refer to as the first order conditions, while this is what we often refer to as the second order conditions. And both need to be true in order for it to be a maximum or a minimum. So for example, suppose that I had e to the x plus x. The question is, where is the maximum or the minimum? We take the derivative of that, which we know is e to the x plus 1. F of x equals this, f prime of x equals this. And for the first order conditions, we set the derivative equal to 0. We then solve for x. Sorry, I meant to do not plus, minus. Again, I meant to do minus there. That's my apologies, but we get the same thing, right? So here, we move the 1 onto the other side. And as you can see, if I take the natural logarithm of both sides, the natural logarithm of e to the x is just x, and that's equal to the natural logarithm of 1. The next question, of course, is that a minimum or a maximum? In which case we get our second order conditions, which says that the second derivative at the natural log of 1 needs to be bigger than or less than, depending on, if it's a minimum or maximum. So if we take the next derivative of this, we get just simply e to the x. And when we plug in the natural log of 1, we get e to the natural log of 1, and that's just 1, which is bigger than 0. What this tells us is that the optimal decision is x equals the natural log of 1, and we know that our scoring metric, as determined by this function, it's going to be the scoring metric is going to be at a minimum, because the first derivative at here is equal to 0, and we showed that the second derivative at that point is bigger than 0, and therefore, according to our rules, that's a minimum. So if x represented, let's say, an order quantity and this represented cost, our best ordering quantity would be the natural log of 1. One last small remark is that if you happen to find the second derivative is exactly equal to 0, you cannot conclude that that point is a negative or a positive, a minimum or a maximum quantity. For example, if I look at the function e to the x cubed, just x cubed, then you'll notice that I have 0 slope here, but it's not a maximum or a minimum. It just keeps increasing, temporarily stops increasing, and then increases again. So the second order condition is extremely important to understand and to test for, precisely because it tells us if it's a minimum, a maximum, or we just don't know.